We always think of our computers as these lightning-fast machines, right? But here's a little secret. Most of the time, that incredibly powerful processor inside is just waiting. In this explainer, we're going to dig into why that is. It's a pretty wild question when you stop and think about it. You've got this CPU, a masterpiece of engineering, that can chew through billions of operations every single second. And yet, when it comes to actually getting things done, it feels like it's constantly stuck in traffic. So what on earth is it waiting for? So this slide right here, it just nails the heart of the problem. Your CPU is like a world-class sprinter, moving at the speed of light, basically. But it's chained to a tortoise, and that tortoise is what we call I/O, input and output. That's the slow, physical world of spinning hard drives and data traveling over long network cables. This massive speed gap is the entire challenge we're talking about today. And if you need to see it to believe it, look at this chart. That tiny little blue bar on the left, that's your CPU actually doing work, thinking, calculating, processing. That giant orange bar, that's your processor sitting around, twiddling its digital thumbs, just waiting for data to arrive. This, my friends, is the I/O bottleneck in all its glory. To really wrap our heads around this, let's get practical. We're going to build a hypothetical server for a pizza shop. I promise this will make all these abstract tech concepts way more concrete and, well, a lot more delicious. But first, we need to cover the basics of how computers even find each other online. Okay, first things first. Every single device connected to a network needs its own unique identifier. Just think of an IP address as the street address for a pizza shop. It tells a customer's computer exactly where on the entire internet to send its order for a pepperoni pizza. But wait, a single computer, a single server, can be running dozens of different apps at once. So if the IP address is the big office building, the port is the specific office number or suite inside. It tells the computer, hey, route this pizza order to the pizza server app, not to the email server or the web browser. All right, so our first attempt at a pizza server is going to be super straightforward. It's set up at its IP address and port. It just waits for a customer to connect, takes their order, processes it, and then hangs up. Simple, right? It works perfectly for exactly one customer at a time. And that, right there, is the catch. And that simple design? Well, it leads us straight into our first massive roadblock, the single client problem. The moment one person calls in their order, anyone else who tries gets a busy signal. Not a great business model. This is the key issue. While our server is handling one customer's order, waiting for them to decide between mushrooms and olives, getting their request, sending back a confirmation, it is totally and completely occupied. No one else can get through. It's blocked. And this behavior actually has a technical name. It's called blocking I/O. The server's entire operation is blocked waiting for that one I/O task, that phone call with the customer to finish. The whole application just grinds to a halt for every single interaction. This is obviously not going to fly for a popular pizza shop. So what's the logical fix here? If one chef can only handle one customer at a time, well, let's just hire more chefs. In the world of computers, this means using something called threads. The way this works is actually pretty smart. You have your main thread, which acts like a receptionist who just answers the phone. As soon as a call comes in, the receptionist immediately hands it off to a brand new thread, a new chef, who can handle that one customer from start to finish. This way, the main line is always free to take the next call. It feels like we've totally solved the problem. But So what happens when our pizza shop becomes a smash hit? I mean, really popular. What happens when it's not 10 customers, not 100, but 10,000 people all trying to order at the exact same time? And this brings us to a legendary challenge in computer science, famously known as the C10K problem. This is the point where our brilliant solution, hiring a new chef for every single customer, suddenly turns into a massive chaotic traffic jam right in the middle of our kitchen. The C10K problem is all about overhead. See, these threads, these extra chefs, they aren't free. Each one uses up memory and, more importantly, takes time for the operating system to manage. When you get to 10,000 of them, the system gets so bogged down just managing all the chefs that it has no time left to do the actual work. And this chart, wow, it shows the ugly truth. The actual work, making pizzas, shrinks down to a tiny little sliver. The vast majority of the CPU's time is eaten up by something called context switching. That's just a fancy term for the operating system frantically running around, trying to give a tiny slice of its attention to thousands of different threads, one after another. To put it back in our pizza terms, it's like having a kitchen manager who spends the entire day just running around yelling at 10,000 chefs, "Okay, you, start working. Okay, now you stop. Your turn. Now you stop." The result is just total chaos, and very few pizzas actually get made. Okay, so using threads was all about trying to wait more efficiently. But the real breakthrough, the truly elegant solution, comes from a completely different way of thinking. What if we could just stop waiting altogether? This is the powerful idea behind non-blocking I/O. Let's go back to the kitchen. The old blocking method is like this. You put a pizza in the oven and then you just stand there staring at it, doing absolutely nothing else until that timer dings. You are completely in sync with the oven and all that time is just wasted. Now compare that to the non-blocking way. You put the pizza in the oven, but then you immediately turn around and do other useful things. You take another phone order, you chop some veggies, you restock the cheese. You just periodically check on the oven to see if it's ready. You're not waiting, you're working. And that is exactly what a non-blocking server does. With just one single hyper-efficient thread, it rapidly cycles through all of its connections, asking a really simple question over and over. Hey, you got data for me yet? Nope? Cool, I'll check back later. What about you? You do? Great, let me process that real quick. It never, ever just sits and waits. And this is a really, really important point to get. The I/O task itself, the data traveling over the network, isn't any faster. The absolute magic of non-blocking I/O is that it lets the CPU do other useful work during those unavoidable waiting periods. This dramatically boosts the whole system's efficiency and how much work it can get done. All right, so let's tie this all together. The simple blocking I/O model is easy to understand, but it wastes tons of precious CPU time by just waiting. The threading model seems to fix that, but it falls apart at a large scale because of the C10K problem. And finally, non-blocking I/O comes in with the elegant solution by changing the whole game from how can I wait better to how can I avoid waiting in the first place. And that leaves us with one last thought. This whole idea of avoiding blocking goes way beyond just servers and code. Think about it in your own life, your own projects. Where are you stuck just staring at the oven, waiting for one thing to finish, when you could be making progress on a dozen other things at the same time?